All right, let's just jump right into it. Welcome to this explainer. Today we're looking at something that is basically a brand new cutting-edge textbook. But this textbook isn't for medical students. It's specifically designed to teach artificial intelligence exactly how to diagnose lung cancer. Here's our roadmap for today. First, we'll look at the lung cancer challenge. Then, building the LungHist700 dataset, followed by how they grade and classify those tissues. After that, we'll get into testing the AI baseline models, and finally, we'll be explaining the AI results. So, part 1, the lung cancer challenge. To put things in perspective, in 2022 alone, lung cancer claimed 1.8 million lives globally. I mean, that is a staggering number. It makes it the most lethal cancer by a really wide margin. It actually accounts for a fifth of all cancer deaths worldwide, killing way more people than even the second deadliest, which is colon and rectum cancer. And really, the whole issue comes down to time. Catching this disease early, that's the absolute key to survival. If you catch early-stage lung cancer, the 5-year survival rate is amazing. It can actually exceed 90%. But if it's caught at a late stage, which is sadly when most symptoms actually show up, that survival rate just plummets to less than 10%. That massive drop is exactly why developing faster, hyper-reliable, AI-assisted diagnostics is so incredibly urgent. We have to identify these microscopic malignancies as fast as humanly or artificially possible. Moving on to part 2, building the LungHist700 dataset. Okay, so here's where the dataset methodology really matters. Past datasets, like LC25000, usually relied on artificially augmented images just to bump up their sample numbers. But there's a big problem there. When you lack traceability from an original image to an augmented one, it confuses the AI during testing. It causes something called data leakage. Basically, the AI ends up cheating. It memorizes the artificial patterns instead of actually learning the real pathology. So to fix this, researchers built the LungHist700 dataset totally from scratch. They pulled 691 authentic, original, high-res tissue samples. We're talking 1,200 by 1,600 pixels from 45 real surgical patients in 2023. And every single field of view was meticulously selected by a specialist pathologist. No shortcuts whatsoever. The dataset is smart. It hones in on the two main subtypes of primary non-small cell lung carcinomas. On one hand, you have adenocarcinomas, which show microscopic glandular-related tissue architecture. And on the other, squamous cell carcinomas, which show observable squamous traits, things like intercellular bridges and keratinization. Telling these two apart is absolutely critical, right? Because in today's world of personalized medicine, different genetic mutations need very specifically targeted therapies. Now, to make sure every single page of our AI textbook was completely accurate, the human experts used this rigorous step-by-step dual evaluation process. First up, image extraction. A pathologist grabbed representative images at both 20 times and 40 times magnification. Next came the morphological analysis, basically grading the stained tissue structure to classify the well and moderately differentiated samples. And finally, for those really tricky, poorly differentiated samples, they didn't just guess. They used advanced immunohistochemical tests, chemical markers like TTF1 and P40, to confirm the exact tumor type. Which brings us to section 3, grading and classifying tissues. Following some very strict medical guidelines, the tissues were broken down into 7 distinct classes based on their differentiation levels. So both adenocarcinoma and squamous cell carcinoma are split into well, moderate, and poor differentiation. You add in a baseline class of normal lung tissue, and boom, there are your 7 classes. As you can see, they are beautifully balanced across both magnification levels. And when you look at it visually, it's pretty wild. Notice how the cellular structure literally breaks down and gets way more chaotic as you move from the well-differentiated tumors, which, still have some recognizable structure to them, over to the poorly differentiated forms of cancer. Those basically just look like completely unrecognizable sheets of abnormal cells. Naturally, the dataset also includes these pristine images of normal lung tissue. Because these are from surgical patients, the images show the specific areas where the tumor hasn't spread. Having this baseline is absolutely essential. The AI needs to know exactly what normal looks like so we don't get false positives. All right, section 4, testing AI baseline models. So the researchers put this flawless dataset to the test using 2 different AI baseline models to see what worked best. First, you have a standard deep neural network, or DNN. Think of this as looking at the big picture. It resizes the whole image and learns the patterns globally. The second approach is multiple instance learning, or MIL. This one is kind of like looking through a magnifying glass. It extracts tiny little patches of the tissue, analyzes each patch individually, and then aggregates all those clues to classify the entire image. These AI models were trained using a well-known architecture called Resonant 50. They did an 80% training, 10% validation, and 10% final test split. But here is the absolute most crucial detail of their methodology, the patient-wise split. The researchers made sure that images from the same patient never, ever crossed between the training and testing groups. If the AI studied patient A during training, it literally never saw patient A on the final exam. This totally stops the AI from cheating, and it guarantees a perfectly fair baseline evaluation across the three main superclasses: adenocarcinoma, squamous, and normal tissue. And the baseline classification results? Honestly, they were striking. The standard deep neural network, when analyzing at 20 times magnification, hit an impressive 90% accuracy. When they bumped the magnification up to 40 times, the accuracy actually dropped just a bit to 82%. Meanwhile, the multiple instance learning method came in at 81%. So the DNN looking at that 20x magnification was the clear-cut winner here. Finally, Section 5, explaining the AI results. When we look at the confusion matrix, you can really see just how reliable that 20 by DNN model is. It correctly identified 95% of the normal tissue and 94% of the adenocarcinomas. It did struggle just a tiny bit more with the squamous cell carcinomas, confusing them slightly with normal tissue. But overall, it proved the model is learning incredibly well from the specific data set. But, a high score isn't enough in medicine. They had to visually prove the AI wasn't just guessing based on random background noise. To do that, they used an amazing tool called GradCam. It's basically an algorithm that creates visual explanations from deep networks. It generates these colorful heat maps to show us exactly which microscopic parts of an image influence the AI's final decision. We essentially get to see right through the AI's eyes. Notice how these heat maps overlaid on the tissue prove the AI wasn't just looking at empty space. It successfully learned to zero right in and highlight the exact clusters of cancer cells. The hot colors show those activation zones. And the best part? When researchers cross-checked these exact masks with human medical teams, the results validated perfectly. The AI was looking precisely where a highly trained human pathologist would look. This just brilliantly illustrates the impact of the LungHist700 methodology. Because the foundational data set was structured so rigorously, without any data leakage, the AI learned the right lessons. It learned to actively target the precise microscopic markers of different lung carcinomas, seamlessly adapting to the visual differences between the glandular tumors and the squamous tumors. It's a massive success. So with high-quality textbooks like LungHist700 paving the way, it leaves us with a really profound question to think about. If this baseline AI can hit 90% accuracy today on such complex microscopic classifications, how soon will your own doctor be consulting an AI specialist to catch diseases before they ever have the chance to spread? It really is an incredible future for diagnostic medicine, and it all starts with cleaner, traceable, perfect data. Thanks for joining me on this explainer.